when I give talks, usually there are more or less 10 people in the room. So I thought this is going to be like that for the rest of my life, which makes me very sad. But then the things got a little bit better a few weeks ago when I presented this work at the WG conference in a small town called Heath near Eindhoven. And it's not a big conference, but there's 30, 40 people in the room. Then I'm very happy there. But now it's getting even better here at this workshop, and there are twice as many people here as that conference. So now I'm extremely happy. So if you don't take anything away from this talk, then just remember I'm extremely happy here. So, okay, so anyway, thank you again for the organizers. Okay, now let's talk about linearly chi-bounding P6C4 free graphs. So this is a joint work with Serge Gaspers. And the outline is as follows. So we will motivate our research by telling you what chi-bound family is, and then show you our result and give you a proof of that using a new decomposition theorem we proved. And then in the third part, I will tell you a little bit about decomposition theorem and how we prove this. And we will conclude the talk by giving you a couple of open questions. Okay, so take a graph G, and as usual, we denote by chi of G the chromatic number of G, and omega of G the clique number of G. And trivially, the chromatic number is at least as large as the clique number. So the question now is, can we upper bound the chromatic number in terms of the clique number? And it turns out, no, you cannot do that because of Gyárlás's large girth and the large chromatic number theorem. So which states that there exist graphs of arbitrary high girth and arbitrary high chromatic number. So if the girth is high, then the graph is triangle free and the clique number is 2. But those graphs can have arbitrary high chromatic number. So there's no way you can upper bound chromatic number as a function of the clique number. But this is not the end of the story. The negative answer just says you cannot do it for general graphs. And the natural question is then, how about graph classes? And this motivates the following definition, and Irene already mentioned in her talk. So we say a class of graphs is chi-bounded if there exists a function such that for every graph G in this family, the chi of G is at most f of omega of G. And this function is called chi-binding function for this family. So this is a really nice notion because it generalizes the well-known perfect graphs. So if you think for a moment, the class of perfect graphs is nothing but a chi-bounded family where the identity function is a chi-binding function for the perfect graphs. So and one class of graphs that has been extensively studied in the past decades is the so-called H-free graphs. And so you fix any graph H and you consider the graphs do not contain H as an induced subgraphs, and those graphs are called H-free. And Gyárlás made a famous conjecture in the 70s that for every forest T, the class of T-free graphs is chi-bounded. So you may wonder why the conjecture only talks about forests. What about other graphs? The thing is, if this fixed graph H contains a cycle, then it's not difficult to see that the corresponding H-free graphs is not chi-bounded, again using Gyárlás's large girth, large chromatic number theorem. So for H-free graphs to be chi-bounded, so H is necessarily a forest. And this conjecture just says that the necessary condition is also sufficient. And what do we know about this conjecture? Well, we know that the conjecture is true for paths, which was proved by Gyárlás himself, and also for trees of radius at most 2, and special trees of radius at most 3, and very recently by Chernovsky, Scott, and Seymour, two-legged and caterpillars and double-headed brooms. I don't even know what they are. So other than that, very little is known, and it seems really difficult to prove the conjecture. Another bad news is that even if you can show that for those kind of T, the corresponding T-free graphs is chi-bounded, the bounds are usually exponential. And around the same time, Gyárlás posed a meta question which asks us about what kind of graph classes admits polynomial chi binding function. So of course, it would be nice to improve those exponential bounds to polynomial bounds, but that seems also difficult. However, if you forbid something more, in addition to forbidding a forest, then it's possible to derive polynomial bounds, or you forbid trump configuration, as you see. So, for example, if we forbid a pass on 6 vertices, P6, a pass on 6 vertices, and a gem, so a gem is just a special graph on 5 vertices, which so there is induced P4, and you have a vertex adjacent to everybody in this P4. So that's the gems, and you can do it. You can get 8 omega, and if you further restrict to P5, then you get 4 omega, and for P5, C4, so C4 is just a cycle of length 4, and you get 5 over 4, and for P5 butterfly, P5 hammer, it's cubic quadratic bounds. And if you forbid something like linear forest, like P2 plus P3, so it's an edge and disjoint an edge, disjoint union of an edge, and a path of length 2, then you again get cubic bound. And if you forbid 2 independent edge, so you get quadratic bound. And again, if you further restrict this graph to be C4 free, then you get linear bounds. So the list is by no means exhaustive, just to give you an idea what's going on in this area. And I have to apologize that I have to apologize for not citing the relevant references here. And the important thing here is none of the result is mine. So for this talk, we will see that for the class of P6 C4 free graphs, we have this 3 half bound. So, okay, let's state this result formally. So we show that for every P6 C4 free graphs, the chromatic number is at most 3 half times the clique number. And I do want to give you a proof of that, but before that, I'd like to point out first, the bound is tight, and it's achieved by several graphs, such as C5, 5-wheel, the Peterson graph with a universal vertex, and some other small graphs. And second, this result unifies several previous results on 2P2 C4 free, P5 C4 free, and P2 plus P3 C4 free graphs in terms of the existence of linearly chi binding function. So before that, it was not known whether this class of graphs admits a linear chi binding function. And we gave an affirmative answer and derived a fairly good bound here. Okay. So the main tool we use to prove this theorem is the following decomposition theorem we proved in the paper, which states that for every P6 C4 free atom, either contains a small vertex or has some special structure, in which case is the join of a clique and a blow-up of the Peterson graph and some special 9-vertex graph. So there are lots of terminology here, and let me explain them one by one. So when we say a graph is an atom, it just means that the graph do not contain clique cut sets. So no clique cut sets. And so what is a clique cut set? The clique cut set is just a vertex subset which induces clique, and if you remove it, you disconnect the graph. So I think Irony already had a very good picture in her talk. So basically you have subset which induces a clique. Then if you remove it and you get, yeah, that's not here. So you have a vertex subset, and you remove it, you disconnect the graph. But the edges between them can be arbitrary. And so what is a small vertex? So the small vertex just means that the degree of vertex is not too big. In our case, not too big just means the degree is at most 3/2 times the clique number of G minus 1. Okay? And the blow up, so blow up is defined as follows. You take your favorite graph, say C5, then you just replace each vertex by a clique, and the resulting two cliques are complete, which means there are every possible edge between two cliques if the original two vertices are adjacent in the original graph, and it's anti-complete if the two vertices in the original graph are not adjacent. So if you take C5, and then you blow up, then you replace by each vertex by a clique, and what you get is something like here. So these so consecutive cliques are complete to each other, and non-consecutive cliques are anti-complete to each other. So and the join, so the join is just binary operations on graphs. So you take two graphs, G1 and G2, and so the join of them is just by adding every possible edge between them. Okay, so we have this decomposition theorem, which is nice. How do I know that? Because if you ever encounter Peterson graphing or research it, then that must be nice. So, but still, this theorem here is not very transparent. What do we have here is, so of course we talk about P6 C4 free graphs. So the assumption is here, so it's P6 C4 free, but we also now assume that the graph is an atom, so which means no clique cassette. And then our decomposition theorem have two outcomes. So first, either you have has a small vertex, so which means a vertex whose degree is not too large, so the neighbors is at most 3/2 omega minus 1, or the graph has a very special structure, so which is the joining of a clique and the blow up something here, and here is just a blow up of the Peterson graph or a special graph. So you can forget about F. You can just think about Peterson graph. So here, right. So either you have small vertex or the graph looks like this. Okay, now I want to give you the proof of this 3/2 bound using this decomposition theorem. So we just use induction on the order of G, and we note that the inductive hypothesis applies when one of the following holds. So if G contains a clique cassette, then what you do is, like here, if G contains something like that, so you have two disjoint subgraphs, and we take the union of these HIs with K, we call this subgraph G1, and we call this subgraph G2. And then note that each of these subgraphs has fewer vertices than G, then by inductive hypothesis. So you can conclude that you can color these subgraphs with 3/2 the clique number of these subgraphs. And by taking subgraphs does not increase the clique number. So this is at most 3/2 omega G. Now, on the other hand, it's well known that if you can color G1 and G2 using K colors, then it's possible to obtain a K coloring of the whole graph G just by permuting the colors on the cliques. So that is to say the chromatic number of G is just the maximum of the chromatic number of G1 and G2. And therefore, it's at most 3/2 omega. So, and if then you're happy if G contains a clique set. Now, if G contains a universal vertex, so we just remove it and inductively color the remaining of the graph. And the key thing here is removing a universal vertex decreases the clique number by 1. So in the inductive hypothesis, you get additional 3/2 colors, but you only need 1 color for that vertex. And therefore, you're happy. And now, if G contains a small vertex, then again, we just remove the vertex, inductively color the remaining of the graph. So small vertex, so G minus V is at most 3/2 omega G minus V. That's the inductive hypothesis. Again, this is the most 3/2 omega G. Now we are almost good because we use this 3/2 omega colors to color almost the whole graph except this vertex V. But luckily, because V is small, V has at most this many numbers. But we have this many colors. Therefore, there's always 1 extra color for V. So we just assign that color to V and extending the coloring for the whole graph. And okay, now let's assume that none of these 3 things happened. And then we look back to this decomposition theorem, say, well, we know the graph cannot contain clique sets, so the graph is an atom, so the assumption is met. And there are 2 outcomes. And we know the graph cannot contain small vertex, so this is not possible. And therefore, the graph must have this structure. But again, note that if this, I forgot to mention this, in this structure, this clique is possibly empty. But if it's not empty, every vertex here is a universal vertex. So therefore, this cannot happen as we showed here. So what the decomposition gives us is that really the graph now, so the decomposition really says G is just a blow up of Peterson graph or the other 9 vertex graph. Okay. Now, in this case, we are also able to show that the chromatic number is at most 3/2 omega G. So the second implication requires a little bit argument. But idea is, say, suppose you have Peterson, and you replace each vertex by a clique of size 2. Then how do you color this graph, right? So if you do that, then the resulting graph has clique number 4. And you just need to color it using 6 colors. Then what you do, basically, the graph is just by pasting 2 Petersons together. So you just pick 1 copy of the Peterson, and you color it using 3 colors, and you color the remaining copy using another 3 colors. Therefore, in this way, you can color this blow-up of Peterson using these 3/2 omega colors. Of course, you don't have to blow up each vertex into a clique of same size. So, but there requires some detailed, careful argument, but that's not very difficult. Okay, so that's the proof of the main theorem, and I still need to tell you how we prove this decomposition theorem. So here, this is our decomposition, and the very high-level idea is as follows. So we just assume that G contains a C6, a cycle of length 6, and we want to argue the theorem holds in this case. And then similarly, we assume G contains C5, and we strive to argue the theorem holds in this case. Then the remaining case is just that G is C5, C6 free, because the graph is also P6, C4 free. That means G does not contain any induced cycle of length at least 4. So the graph is chordal, and it is well known that every chordal graph has a simplicial vertex, i.e. a vertex whose neighborhood induces a clique. So the degree of that vertex is just at most omega minus 1, which is small. And the difficulty is, however, in order to make this work, we need to eliminate two more special graphs, F1 and F2 here, and do it in the right order. So if you follow this approach naively, say you assume G contains a C6 and try to analyze the structure of the graph, and at least we were not able to show that this theorem holds in this case. So instead, we first assume that the graph G contains this special graph F1 as an induced subgraph. Then we analyze the structure and see how the remaining vertices attach to this subgraph. And we were able to show that the theorem holds if G contains F1. Afterwards, we can just assume that G is also F1 free in addition to being P6 C4 free. And with this additional information, we were able to handle C6. And then we move to F2, and similarly, we handle C5, and therefore make the whole approach work. And I don't think I have any time for any details of the proof of the decomposition theorem, but I think they're not important anyway. So it's nice we have this 3-half bound here, but unfortunately, our inductive proof is not algorithmic. In other words, we cannot directly transfer our proof into an algorithm. But we still managed to get a polytime 3-half approximation algorithm using a little bit more trick. So that means we can color a P6 C4 free graph using 3-half omega colors in polynomial time. And also, as a corollary, because even-hole free graph and the P6 free graph are a subclass of P6 C4 free graph. Therefore, we get 3-half bounds for these subclasses as well. This is sort of interesting because there is a known result on even-hole free graphs. For even-hole free graphs, the bound is 2 omega. So the chi is at most 2 omega for even-hole. So I will just finish by giving you these 2 open problems. So we did this 3-half bound for P6 free, and the natural questions, can you do it for PT C4 free for general T? And also, can you extend this even-hole P6 to even-hole PT free in general? Okay, thank you.
Are there any questions? No. Oh, Nishan?
Yes.
Did you choose P6 and C4 expecting that you would see Peterson there, or was it?
Okay, yeah. Actually, there was a known result on the structure of these graphs, but the result is about C6. So they assume C6, and they assume that C6 is not dominating. And that's where the Peterson graph comes from. But in order to have this decomposition, we need to extend their analysis significantly. Yeah.
Any other questions?